Now we already talked about the relationship between limits and continuity when we talked about continuity. We wrote down the formal definition at one point, I believe, just because we were talking about limits in general. And remember, on the very first day of the course, we were doing piecewise functions, and we just sort of informally inspected graphs to determine where they were not continuous. So we have to have a general idea of what it means for a graph to not be continuous. And for a graph to not be continuous, it's like not a straight line that goes at a particular point. It's not a straight line that goes, or not straight, but a line that goes through the point. Like literally the word continuous, right? And we're going to talk about all the different reasons why it would be continuous, what they look like, that kind of thing. That's what we're doing today. Who can outline, just in words, not formally. We're going to do it formally. I don't know why I have this note organized the way I do. We're like, talk about it once, and then do something else and talk about it again. We're going to do the formal definition after. Just informally. What's the relationship between limits and continuity? How would you describe it? Or describe anything about limits, even just to get us started. What do you think? Okay, so there might not be a limit. Good. What else?
If the graph is continuous, you can sum it.
Okay. Yes, I think that's probably true. Yep. What else? Pop out with the same x value. Is that what you said? Yeah, okay, so now we're getting very close to this. It wouldn't even be a pop out then, though, would it? Interesting, right. So we're getting closer. Okay, so we might say, let me summarize what we're saying here. Whoops. If the value of the function at some point, we typically talk about the continuity of the function at a point. We sometimes do summarize more. We will even today, but like generally speaking, we're looking at a particular point, that we might think it's not continuous. Okay, if a value of the function at a point is equal to the limit of the function at that same point, then the function is continuous at that point. We've already written that formal definition. We're going to write it again in a minute. Okay, there are three types of discontinuities. What do you think they are? And apparently discontinuities is spelled wrong. Hopefully you spelled it right. You probably did. Can anybody give me one? Generally speaking, your intuition will be correct in a lot of this today, I would imagine. So whatever you think maybe is one of the discontinuities probably is. All right. Yeah, very good. So we're going to call that a break. Hope everybody got that other part down. So the first one will be a break, which is like a pop out. That doesn't actually include a whole pop out or a jump. And there's another, and these aren't technical terms, so different textbooks use different terms. I can't remember. There's another term that one of the textbooks uses, and it's evaded me today. I can't remember what it is, but okay. So it's some kind of a jump or a pop out. We're gonna sketch these in a minute, one at a time. What else? Will be another type. If the limits don't exist. So jump would be that case. We're going to look at these as well. What would be another situation where the limit doesn't exist? Maybe the left-hand limit and the right-hand limit aren't equal. Yeah, very good. So a vertical asymptote. Vertical asymptote. And what's the third one? It's actually already been said today. Somebody said it. A hole. So algebraically, these are different. So that's why these are the three different types. This is going to be confusing when we talk about the three different cases next. But we'll talk about that more when we get there. Okay, so I'm gonna now do an example of each of these, or we are going to together. So the first one, which is a break, would typically occur, not always though, in a piecewise function. So up to 5, so I'm going to mark 5 here. And that graph would look like that. So that's a jump. It's jumping from one place to another. Do you remember the one that we saw on Monday? It was in our lesson, and it was something like this. And I can't remember, exactly, but so this has an asymptote at 2, and I think it did something like this. Might have gone down, I can't remember, and then it went like this, and then it went like that or something. That's not quite right, but it was something like that. So these strange, and we didn't graph these in advanced functions, right? When absolute value inside with a rational, but we just graphed it with technology. I happened to graph it with technology on Monday, and this function naturally has a jump in it, which is interesting. And that's not really something we've seen before. Usually jumps are artificially created with like a piecewise function type thing. Okay, good. What did we say type 2 was? A vertical asymptote. So a vertical asymptote might just look like this. X cubed minus 27 over x plus 3. So this has a vertical asymptote at x equals negative 3. And I'm just going to draw the vertical asymptote part. Oh, and that's because I'm going to show this too. Oh, no, that's the next one, sorry. And the third one was a hole. So I'm going to change this up just a little bit because I think it kind of nicely highlights. What if it was x minus 3? Well, then it's a hole. Very similar equations, but this one's actually a hole because it would be x minus 3 times x squared plus 3x plus 9 over x minus 3. So this has a hole at positive 3, and it would be something like that. So the three types of discontinuities: a break, vertical asymptote, and a hole. We know what they look like algebraically, typically, and that's one of there's two types of questions from today, and that's one of the types, is you're given a function, and you have to analyze it, and you have to think, where might there be a discontinuity, find out if there is, and describe what type it is, like why there's a discontinuity there. And vertical asymptotes and holes, from all the work we did in Unit 5 in advanced functions, we know what they look like algebraically just in a function. Typically, it's when you have some kind of factor in the denominator of a rational function. And it might be a vertical asymptote or it might be a hole. You got a little bit of work to check it out. And if it's going to be something else like a pop-out or a break or something like that, it's probably going to look for us like a piecewise function. And so the work required to determine that will look a little bit different. But it all has to do with our understanding of looking at an equation and sort of being able to examine it and think about where might it be discontinuous. Any questions on that before we move on? Okay, this is our rewriting our formal definition, although we're including an extra little part to it, which is redundant, but we're doing it for a reason. Function is continuous at x equals a. So again, notice that we're just talking about a particular point. One particular value, a, might be 2, might be 3, might be pi, might be negative pi, could be whatever. Okay, at a particular value. If and only if, so this is the redundant part. The function is continuous at x equals a if and only if the limit as x approaches a of f at x exists, and that limit equals f at a, the function at that point. Does that make sense? So if the limit as x approaches a of f at x equals f at a, it has to exist. The limit can't exist and then also equal something. Okay, so that's why to me this is redundant, but there's a reason why we're including it, because it's going to be part of our thinking of whether or not the limit exists. Stop me if there's questions. We're going to keep going. For discontinuity, 3 cases for discontinuity. Everybody good? The first one is f at x does not exist at x equals a, or f at a does not exist, same thing. When will the function not exist at a point? What's one example of that? A hole? What else? Vertical asymptote. Obviously both at x equals a. If you have a piecewise function that has a hole, like, I'm just scrolling up here for a second. Like, imagine this was missing, and it was x less than 5, x greater than 5. That would be like a jump, so it would be a break, but it would also have a hole because this point wouldn't be included, so it would kind of cross over into different types. that would be considered a hole in the graph. But otherwise, where did that go? There. This function does exist at 5, right? So this is not our case number 1 here. That piecewise function does not fit with case number 1. So what would that look like? It's always good to draw a sketch. Ooh, I'm going to fix that. Kind of looks like sine curve. That's what a hole might look like. We've never seen a hole in a sine curve, but it doesn't mean you can't have it. Or vertical asymptote. So that first case is the function does not exist. Next case, the limit as x approaches a of f at x does not exist. When would this occur? Asymptote again. What else? So a hole, the limit might exist. Yeah, so a break that has a jump in it or something like that. Good. And this is when the left-hand limit doesn't equal the right-hand limit. Also, like if a graph is just starting at a point. What graph starts at a point? So the function exists, but the limit wouldn't, because it might not even have a left-hand limit. Square root function. We don't really talk about that one very much, but like it doesn't have a left-hand limit where it starts. That's a couple of sketches here. And vertical asymptote again. And what about a jump? So notice again the function exists. At all those points, but the limit doesn't exist. So it's a different case. Okay, in case number 3, what's left? So if it's not case number 1, which said f at a does not exist, then in this case, f at a does exist. And if it's not case number 2, where the limit doesn't exist, then the limit as x approaches a of f at x does exist. So what would be the case for discontinuity? Right, so they both exist, but they don't equal each other. And that's that formal definition of continuity, which again, if you think about it, we didn't say this, but that's why we included the limit exists, because that's one of the cases. The function also has to exist at that point. Again, that kind of goes without saying. The function doesn't exist at some point. It's not continuous, but that is one of our cases. So don't get confused, the three different types with the three different cases. There's a lot of overlap there, but make sure you understand which one is which. And what would it be? What would be this situation that would occur where the function exists and the limit exists, but they don't equal each other? I think there's only one situation where this would occur. Anybody? An idea?
Is it a hole?
So it would be a hole in that the limit would exist at a hole, but the function also has to exist, so pop out. So it's got to pop out and exist somewhere else. So that's basically the only situation I can think of. Very good. Everybody got that? Okay, so now we're going to do a few examples of this type of question. I think 3 examples of this type, and then 1 example of the other type. Like I said, there's sort of 2 types of questions that you're asked about continuity, and they're obviously there's overlap and they're related, but they're different. You want to recognize them both. They'll both be on the test. I'll tell you that right up front. Find the value or values of x at which f at x is discontinuous and state the type of discontinuity. What kind of a function is this? Where might it be discontinuous? In fact, we know a lot about it, so we know that this is continuous. Let's not beat around the bush here, right? We know that this is going to be discontinuous. At what value? Where is it discontinuous? Okay. At 4. But we don't know the type. Not yet. Okay, but we know it's going to be discontinuous at 4. And it'll be either what? Like there shouldn't be any guessing here. It's going to be one of 2 types. And there's only 3 types. It'll be a hole, or didn't we ever graph? We've graphed this before, right? Did we ever graph pop-outs? Why would it have a pop-out? So either a hole or. Okay. Now, if you've already done the work and you know which type, that might be why you're wondering. But just by inspection, when I have a rational function, it's either a vertical asymptote or a hole. And we just have to figure out which type. Is it discontinuous anywhere else? Were these functions back in Unit 5, were they discontinuous anywhere else? The answer is no. Okay? Don't wonder, don't second guess yourself. If you're not sure, go back and think about it. But the answer is no. So what are we going to do to figure out what type it is? I hope that's fairly obvious. We're going to factor. So I get 4 plus x and 4 minus x over x minus 4. And this is what I was saying before. These are not the same thing. So you cannot cancel those there. But what can you do? Joel? So think about this. 4 minus x is the same as negative 4 plus x. If I distribute the negative back in, I get back that original thing. And that's algebra. That's math. You can any 2 things that are equal, you can replace one with the other. And what is another way of writing this? Negative x minus 4. And that's why we want these written in proper form, not 4 minus x and not even really 4 plus x. 4 plus x isn't wrong, but so I'm going to rewrite this as negative x plus 4 x minus 4 over x minus 4. Okay, and therefore we say, therefore, f at x is discontinuous at x equals 4 because there is a hole. Don't say it any other way. There's a few things that are formalities today. Our very last question is even more formal, but don't change that up. Don't be lazy. and change that statement. It should be stated exactly that way. Because there is a hole, because of a hole, and that part I'm not as particular about. But you have to say it's discontinuous, you have to say where, and you have to say the type. And it should be like in a sentence. Got it? Good? Yes? All right. Let's move along. There's a printing error in this one. There should be an X there and a 0 there. What might be happening here? Again, this is the kind of thing that we graphed a lot of last semester. So we know a lot about it. And we know that it's going to be discontinuous when the denominator is 0. But in order to determine the type, we got to factor the whole thing and do all of it. So you can go ahead and try that one. You can tell me what's happening here?
There's a hole.
There's a hole? At 5, good? Is that all? And there's an asymptote at? Good. So we're going to say both. Therefore, f of x is discontinuous at x equals 0 because there is a vertical asymptote and I'm going to do it down here. F of x is discontinuous at x equals 5 because there is a hole. Happy? Satisfied? Comfortable with that? One more of these types that's a little bit different. This stuff is so familiar to us, I hope, from last semester that, like, that's pretty straightforward, pretty easy. Yes, there's a formality to it of how I want you to state your final answer, but it's pretty straightforward. This one's a little bit different because it's a little bit new. And again, this is the first type of question. After this one, we're going to do the second type, which is even more formal. And the question is worded differently. So what's happening for this one? Like, remember the last 2 examples were rational functions. And what we know about rational functions is that they don't exist when the denominator is 0, which means it's either a hole or it's a vertical asymptote. What do we know about this one? Just by looking at it and what we know about functions. Am I? Yeah. Where might that be happening? For this one? At 1. But what about the rest of it? What about anywhere else? Is it going to have anything wonky going on? I don't think so. What about, so less than 1, everything looks like it'll be totally fine and continuous. Greater than 1, everything will be continuous. We just have to check at 1. I don't think we ever have done a question like this, but what if there was a question like f at x equals, and it was like 1 over x, and x squared plus 3 or something like that. Like what if it was piecewise and one of the parts had a rational component to it? Well, then you'd have to do the rational component and you'd have to check the other part. Now, if this could get interesting. X less than -1, x greater than or equal to -1. Well, now function is interesting. Isn't in the domain where we're using that. You know what I mean? So like you would have to really think about it. Not like I say, we don't usually ask questions like that, but it would be interesting. You could look at that case. So how are we going to do this? If you were doing it totally informally on your own, you could just plug 1 into both those parts and see if it's the same value, right? But because this is a bit more of a formal process than that, technically I can't substitute 1 into here because the function doesn't equal that at 1. It equals this at 1. So it would look weird to sub it into both. Do f at 1 twice. Do you see what I'm saying? So instead, we can use limits to get past that. So we're going to do a left-hand limit and a right-hand limit. And once we use limits, we're not talking about the value of the function at that point. We're just talking about the function as it approaches that point. So we're going to do the limit as x approaches 1 from the left of f at x, and the limit as x approaches 1 from the right of f at x. And as I approach 1 from the left, this is where x is less than 1, so I'm using this quadratic part, that first part. These usually should be written in order. They may not always be, especially if somebody else writes it, or for some reason it was written in a strange order, but usually sort of from left to right along the graph it's written that way, right? But so this is x squared minus 2, and so then I just sub in. And as I'm approaching from the right, that's when x is greater than 1, so I'm using this part. And this is what I mean. Normally, subbing 1 into this wouldn't make any sense because the function doesn't equal that, but when you're doing limits, you can get away with it. So what happened? Interpret this for me. Abdul? Yeah, nice. I like that. So we're always going to make that statement. Which means the limit does not exist. Which means what? Discontinuous at x equals 1 because there's a jump, right, or a break. Very good. So therefore, f at x is discontinuous at x equals 1 because there is a jump. Maria? You'd have to check them all. Mm-hmm. Like if there is more lines to this, yeah, you'd have to check them all. You're finding all the points of discontinuity. Okay, so that's question type number 1, where it just says determine where the function is discontinuous and state the type of discontinuity. And again, we start with our understanding of looking at this and thinking where we know it's not discontinuous and where it might be discontinuous and sort of checking to see. Hi, what's up?
What's our head count?
Going on anyway. Yeah. Yeah, okay. Okay, we got 1 left. We got 12 minutes. And this is the one that is an absolute formal process. It's almost like a proof. So you're going to notice I'm going to make a big deal about exactly how you say all the different parts. And you'll notice how it's different. There's a lot more to this one than the other one. Because the other one was just looking where it's not continuous. This question will be worded one of 3 ways. Really one of 2 ways. It will say, give a detailed discussion of the continuity of the following function. or it will say show a formal proof regarding the continuity of the function. Detailed discussion or formal proof, and it's this type of question that we're about to do now. Formal proofs, formal processes are not the time to be lazy and make up your own way of doing it because it's too much writing the way your teacher does it. That's just us tossing marks away. It has to be done exactly the way that we're going to do this one. And you want to make sure you understand like why, like how it's different, exactly what you're saying. Everybody got this copy done? I want to make sure you're with me. So put your pencil down for a second and think. Again, we often think about a graph where we start at the left, so this is your left, and we go across the graph and we sort of think about what it looks like as we go across the graph. Okay? And that's how I'm going to think about this. So I'm going to start way off to the left, which means I'm using this part because it's less than 2. So I'm starting with this. And I'm saying to myself, what do I know about the graph when I go way off to the left, like to negative infinity? Is the graph continuous? What do I know about it? What does it look like?
It's continuous and going positive.
Good. And why is it? How do you know that?
Because it's positive x, like it's not left and it's parabola.
It's a parabola, exactly. It's a quadratic. And in other words, it's polynomial. And polynomials, we know, are continuous everywhere. If it was a rational function, like I said before, this would be different. It's polynomial. So we know that it is continuous everywhere. So for x less than 2, f at x is continuous because it is a polynomial. Now, we're not actually going to do it all in order. I'm going to skip over this. Like, in other words, like we talked about before, we know there's only one interesting point to this graph, right? But we're going to make a statement about all other points. So I know it's continuous. I'm saying it's continuous, and I'm saying why. Then I'm going to say for x greater than 2. What kind of a function is that? Linear, which is also polynomial. So if you say linear or say polynomial, both is fine. F at x is continuous because it is a polynomial. What other kinds of graphs do we know about? Like we know trig graphs. If it was a sine curve, they're continuous everywhere. Like we know about other graphs too, right? Remember the cases for discontinuity. One of them is f at x does not exist at a. So I've handled every point less than 2, every point greater than 2. Does f at 2 exist? Yes, it does. I'm going to state that f at 2 exists. Why? Because it says x greater than or equal to 2. This says it exists at 2. I can evaluate. I put 2 in. 2 minus 2 is 0. It exists at 2. What is left to show? The limit has to exist, and the limit has to equal the function value. And that's what we're going to do next. Notice, everybody eyes up and watch. Right here, I did not put x greater than or equal to 2. Why? Because I don't know that it's continuous at 2. That's what we're about to check. If you put this, you're wrong. You're going to lose a mark. That is incorrect. We only know for less than 2 and greater than 2. We know it exists at 2. Now we got to check and see what else is going on.
But does that mean that at f at 2, it's not a polynomial?
It is, but it may not have a left-hand limit that equals the right-hand limit. Yeah, that's a tricky question because we're saying it's polynomial here. So I think you would say it is a polynomial, but we also know that's where it ends and starts to become somewhere else. Yeah. Okay, so let's do the left-hand limit and the right-hand limit. The limit as x approaches 2 from the left of f at x. The limit as x approaches 2 from the right of f at x. Go ahead and do that. I don't think you need my help. From the left, I'm using that one. And from the right, I'm using that one. And look what we got. So now we have to interpret this. And again, just a heads up, following is a whole bunch of different statements that are required. We're getting a little bit short on time, so I'm going to hope that you're with me. And I'm going to write down all the different statements. Since the left-hand limit equals the right-hand limit, the limit as x approaches 2 of f at x exists. Now, what is f at 2? Again, watch, I'm going back up here, and I'm saying this is where I'm including the point 2, so I'm using this one to evaluate it. You wouldn't have to show the substitution. I'm going to, just to make sure that we are all aware of exactly what's happening here. So this is like 2 minus 2, which equals 0. I know we already did the math here, right? So you could just say f at 2 equals 0. The limit exists. The function exists. We already determined that. Now we have the value of the function. And now we can say, therefore, the limit as x approaches 2 of f at x equals f at 2, or equals 0, which equals f at 2. Right? The limit of f at x exists, it's equal to 0, which equals f at 2. Therefore, what? It's continuous where? At 2, very nice. Therefore, f at x is continuous at x equals 2. One final summary, take a look. F at x is continuous for less than 2. F at x is continuous for greater than 2. F at x is continuous at 2. What does that mean? Where? Everywhere, exactly. That's the word I'm looking for. It's continuous everywhere. Do you have to say that? Absolutely. If you have different parts that you did one at a time and then they get connected, you restate that overall part. This is similar to something we did last semester, but anyway, I'm just going to jump to this. Therefore, f at x is continuous for x is an element of the real numbers everywhere. We're not just using the word everywhere, we're using proper notation as well. F at x is continuous everywhere. And you're often asked to draw a sketch of these. So this one goes something like this, I think. For the final time, You have to restate this because the different parts were connected. I don't need to be drawing the conclusion for you. Less than 2, greater than 2, and at 2. Those are all connected. We can re-summarize that more clearly, more succinctly, so you must. If it turned out it wasn't continuous, then you would say, therefore, f of x is discontinuous at 2 because there's a break or a jump, and you would be done. You wouldn't have to go and restate what you already stated. It's only because the different parts became connected that you had to do that.